Okay. Hello, everyone. Welcome back to Calculus 1000. Today we are starting the new chapter. This is about a notation that we will need to understand or better understand what's called Riemann sum. So there will be few things that will take us one session today to understand about the notation. It's good to have that notation because it simplifies things for us. And then after that, next week, we will start what's called Riemann sum, which is the first step in defining definite integrals. And then we will go into the definite integrals, very similar pattern, basics, then the strong tool, fundamental theorem of calculus, and then we move up onto the applications of integral. We will see a little bit of game, nice things happening. How many of you have seen integrals in your high school courses? Can I see the hands? Okay. Okay, good number. Okay, that's good. Okay, doesn't matter. So this is, we will start from the scratch. We will cover everything that you need to know. If you haven't taken any course covering integral, you don't need to be worried about that. Okay. Today, the title of the lecture will be sigma notation. We are going to work on one notation, and around that we want to understand what that notation means. But in particular, what we will deal with is something like this. You have summation of some terms. You want to find a way to study things like this. Oh, maybe I'm sorry. I should have started with different starting points so that I can give the most general notation that I can. So you will see in Riemann sum, and after that, we will deal with this sums of terms of one function or one expression. You're plugging in different values of integer index, and you're adding them. Well, we want to fix a notation that is a bit shorter, concise, easy, and we want to be able to work with it better than always writing this huge sum. This can be done by what is called sigma notation. So instead of writing that, we will write this nice curly letter there, which is capital sigma in Greek letter. We have lowercase one, this is written different way, but this is how the capital one that we will use. This means add. So if I want to read this, I'll say re-add the terms of fm plus 1 all the way to fn. Now, this is add what terms? Terms that are given by evaluating function on something called the index or the variable of summation. Then you will start and end your index, your variable. You will start it at m, and it will go up one by one until we get to f at n. Yes? The index for sigma always will go up one by one. Now, the notation, I need to fix some wording here. This I is called the summation variable or summation index. This is the starting point, starting index. This is the end index. And sometimes the terms f at I, we call it the summand, but we won't use this notation much. Okay? What I want you to start developing in your mind there is, okay, this short notation has a meaning. That is this whole thing here. For example, have you heard about the story that a teacher asked their school, their student, could you add numbers from 1 to 100? Have you heard that story?
Gauss, right?
Gauss, yes. So teacher come in outside. It's a rainy day. I don't want to teach anything. Let's give them something that will keep them busy for half an hour. Yes, at least. So I asked them, or he asked them, add numbers from 1 to 100. So this is the assignment. And give me the value. Not knowing that, one of his students he's going to be one of the greatest mathematicians of all time. Of all time, yes. His name is Gauss, and poor teacher, before he can settle down in his chair, someone raised hands. Here is the answer. Do you know what is the answer there? Yes?
Isn't it 101 times 50, whatever that is?
So the guy, the way he looks at this is that I don't need to add 1 all the way up. What I need to see is that the first number and last number, when I add, I get 101. Now, the second number and the second last, which is 2 plus 99, they will add up to 101 as well. Yes? So this and that is 101. This guy and the second last is another 101. Then the third one and the last third one, the third one from the end is also 101. So you're adding 101s, but since you're pairing them, there's only 50 of them. So this value is 50 times 101. Or maybe let me write it the way we will write later on, that way. So you make it half of the numbers, and then you add the first one to the last one. You multiply these ones. So if I want to write this in the notation that we fixed, basically what Gauss discovered is the summation formula for this thing, that if I go from I goes from 1 to 100, that's going to be given by that number, which is that the number, I think? Yeah? For now, we will get back to that formula for general case, but I want to focus on this notation. Instead of writing up, adding all those things, I'm going to use this notation. And the first first example we will have, or set of examples, is that I will ask you to write the given sums in terms of using sigma notation. So in particular, what we are interested in is, okay, I see that I am adding numbers of this form. So f of x is x squared. And then I'm adding them from 3, index 3, 4, 5, all the way to 20. So this is I squared, I starting from 3 all the way to 20. That is the notation, sigma notation of that same summation. And I'll give you 90 seconds to go through those ones. Feel free to talk to the person sitting next to you, and please do it. Because if you don't check it, you will do something that at the end, it won't make sense much. But at this point, I want you to familiarize yourself with the idea that I don't need to open up things writing like that. This is equivalent of that, okay? Go ahead, please. 90 seconds starts now.
We didn't even do anything. We didn't even do anything.
20 seconds left. When you're trying to write the sigma notation or reading sigma notation, doesn't matter. This is two-sided thing, yes? What you should do is this, that I look at the terms I'm adding, and I want to find a pattern for that, and then write it in the general form that I can write. In this case, what is the pattern you're seeing? Can I get an answer for that one? What is the pattern you're seeing? Yes, please?
The numerator increases by 1, the denominator increases by 1. Like, what?
I see. I like that observation, that each time we have a fraction, and as we go on, the denominator and numerator will increase by 1. Any other observation for the pattern of that summation? Yes, please.
Denominator is the numerator plus 1.
Denominator is 1 more than the numerator. So in other words, I can say that, oh, forget the denominators for now, and look at the numerator. They start from 1, goes all the way to 100. Okay, that's my summation index. I can start I from 1 to 100, and then I'm adding fractions. How are the fractions? Fractions, numerator is my index. Denominator is the index plus 1. That is the sigma notation. Did anyone get any other pattern for this one? Did anyone write this in different form? One other interesting form to write this is, why do we get the numerators as the index? Why don't we get the denominator as the index? It moves up 1 by 1, starting from 2. So in this case, I can say that my denominator is my index. Starting from 2, going all the way to 101. And the numerator is 1 less than the denominator. So that is j minus 1. That's another way of writing that sigma notation, that sum in sigma notation. Okay? What is the pattern for the third one? Yes, please.
The value under the square root is increasing
By 2. So we have square root of something that increases by 2, and it starts from 7 and ends at 55. Remember, index of summation always goes up by 1. So if something is increasing by 2, that means that there is a formula inside that sigma notation that takes care of that jumping by 2. The notation should go, the index should go 1 by 1. Well, one way to see this is, oh, there are odd numbers. And odd numbers, I can always index them by, this board is getting very complete, very mixed up things. I will write it here. This is awful use of board, but you can see it better this way. So that one I'm writing as sigma of odd numbers. Odd numbers, I can always denote them by 2i plus 1. Yes? 2i plus 1. 2i is even plus 1, that will make it odd. But now, the smallest value of I that will give me 7, or the value that will give me 7 is when you plug in I equal to 3. And then it will go, index going up 1 by 1. But because of this 2, the value under the square root will jump by 2. And I'll get to 55. What index will create 55 using this formula? 2i plus 1 is 55. Then I must be 27. Okay? Yes, please.
Okay, so just do something where it's like root I plus 2.
Root I plus 2. Can anyone see what would be wrong with that? Or is that right? Okay, yes, please. I goes up 1 by 1. Yes? So if you say root I plus 2, it will start, you may start from 5 in your case, but then the next number is 6. 6 plus 2 is 8. I don't have root 8 there.
But I'm saying root I plus 2 like altogether.
That's okay. So when I is 6, 6 plus 2 is 8, root 8. Root 8 is not in my summation. Yes? So yeah, that's not going to cover only odd numbers. Yes, please.
Plus 2i work.
That is another one that I will write here. Also, you could say,
Like E.
you mean 2i plus 1, plus 5. 2i plus 5. I can say that now you can start from 1 and go all the way to 25, yes? That's also another way of writing that. What about the last one? Does anyone see the pattern there clearly? The pattern there? I have 2 to the power something, 4, 8, all the way 10, 48. So I have 2 to the power I. I goes from 2. What 2 to the power, what number is 2048? 2 to the power 10 is 1024. That's the 1 kilobyte, yes? Then another one, 11. So we'll go all the way to 11. Then after that, we have sine of, when this is 2, that is Sorry, okay, yes. When this is 2, that is 5. So that will be I plus 3, and it goes up. One key point for us, maybe I should stop here. Is there any questions? Please ask the questions, because I hear sometimes after the class for this notation, students come in and say that, oh, I just understood the first board that you wrote. The rest, I couldn't see anything. Please ask the questions. Yes, please.
I would, for the one right before this one, like you said that you can't do root I plus 2, because like then you would get like to the even numbers.
Yeah.
Why can't you do root I plus 1 then?
Again, see, since I goes 1 by 1 up, if you don't have 2 multiplied to I, increase of 1 in index, it will increase the thing by 1. So it will cover both evens and odds, no matter where you start, yes? So you have to make sure that you have that jump by 2. That's why it's very necessary to have 2I, yes? Any other questions, any other comments? Yes, please?
I missed how you got like 11.
So I see that the coefficient of sine are 2 to the power something. What is the number that 2 to the power that will give us 2048? I don't know. I just happen to know 1024. Multiply another 2. That's what you get. One key point. One key point about the sigma notation. One very important one. That index I is a dummy variable. It has no meaning when you're using it. So summation index is a dummy variable. Meaning that if you're going with I can take it and replace it by any other variable I want. I by itself has no meaning. The meaning it gets is using the lower, upper, and the function I'm evaluating at. So this could be j going from m to n f at j. So they're completely equivalent. They're doing the same thing, just changing the names, yes? The second thing that you need, or you probably already noticed, is that every sigma term can be written in a form that index starts from 1. Every sigma notation that someone gives you, something like this, you can rewrite it such that the index starts from 1 rather than from, like we had 3. Check this one. We already did this in some cases. Here, this was starting from 3, and then someone suggested something that starts now from 1. We also did it here. We had 2 different ways of writing this in sigma notation. One, the index started from 2. The other one started from 1. Oh, I did do that there. I was thinking. Now, this one, we can also change it to start from 1. This one also, we can change it to start from 1. That's our next work to do, but let me tell you how this happens. So, when you start from m and go to n, f of I, you can write that sigma notation in form that the index starts from 1. what I want you to see here is that I goes up one by one, yes? Now, to start the index from 1 rather than m, what I need is to define this j to be I minus m. M is that constant. But then if the starting point of I is m, this will start from 0. I will add 1 to that. So I am defining a new index, summation index, to be j, and that is how I will change j to I. For example, if I is m, plug it in here, m minus m, 0 plus 1. That's how I get that one. For n, you plug I equal to n. The upper bound for this guy will be that. Now, what about this index here? Because here index appears to be I. Well, I can write I in terms of j. I is j plus m minus 1. I just took this part, take it to the other side, and wrote I as in terms of j. Now, I want to replace I by that expression, j plus m minus 1. This change of index to start from 1 sometimes is important for us because that's how we will able to use the summation formulas that we have. And let us do some examples here. Let's do the first one is the one that we had up there. I goes from 3 to 20, I squared. Write this in a new sigma summation form such that the index starts from 1. Let me write down the other ones and then I will do this. Oh, we already did that one. How about this? Let me write n there. Did we do any? Okay, we can also try to do that lower one as well. I goes from 2 to 11, 2 to the power I, sine of 20 down there, and we had I plus 3. Let me do the first one myself and show the work. And then I'll give you some time to do the other ones. And I always pick the easy one for myself, as I always do. Here, the starting point for I is 3. I want to rewrite this so that the new index starts from 1. Well, you just need to see this. Just shift I to lower values. So in other words, instead of using I, you use I minus 2 as your index. Okay? So that means that my new notation, sigma summation, instead of starting from instead of using I will use j. And now this formula will hold all the time. When I is 3, 3 minus 2, j starts from 1. When it gets to 20, I gets to 20, j will get 20 minus 2 to 18. Yes? How about the term here? Well, I can use this, write I in terms of j. And then I squared now is j plus 2 squared. Why do I need to do this? I will show you in 5 minutes. Because we will have some summation formulas that are given when I starts from 1. If you want to turn it or you evaluate some summations that are not starting from 1, you have to change everything to start from 1 and then use those formulas. I will give you now 90 seconds to do those two ones. And if you do carefully, it will be easy for you to complete that. Okay? 90 seconds starts now. You're trying to rewrite these sigma notations in the form that the index starts from 1. Okay, maybe let's hear one question about what the example we did. Yes, is that about that?
I equals j plus 2.
Oh, how did I go from this to that?
Oh, never mind.
I just solved it for I, because that is a good question. Let me answer it, even though you know it now. So I just solved it for I. I took negative 2 to the other side, and I wrote I in terms of j. Go ahead, please. 90 seconds starts now. Another 20 seconds before I start doing it on the board. This guy starts from 10. I want to turn it to something that starts from 1. So in other words, I define this new index to be my old index, but starting from 1, meaning that you take away 9 from that. So if the first starting point was 10, 10 minus 9 is 1. That's how it starts from 1. And then the upper limit, this is n here. So I is supposed to be at the end equal to n. Then j would be n minus 9. How about the formula? Inside the sigma, or the summand that you're adding up, the terms that you're adding up, you have some i's. Now you have to write I in terms of j, which is just solve that equation that you fixed at the beginning. I is j plus 9. So that will give me 5. Instead of I, I'll write j plus 9 to the power 3 plus 5 to the power j plus 9. Yeah? For this other one, j is I minus 1. So when it is 2, minus 1 starts from 1. When it is 11, ends to 10. 2 to the power, I will be j plus 1. Just solve that for I. And then that will be 2 to the power j plus 1 sine of, this part is 20. Instead of I'll write j plus 1. That will give me j plus 4. Oh, okay. This reindexing is one of the key points when you're working with sigma notation. Another property, you already are familiar with these kind of properties. When you are adding two functions to create that summand, I goes from m to n, then you can add each one on those indices and then add the total sums afterward. Sigma notation is additive, yes? You were asking me the other day. So, and also that scalar multiplication also works here. So you can always try to break it down to smaller pieces and try to evaluate that. Any questions, any comments so far? Other than these properties, I have 5 summation formula that you have to know for this course. And one of them is the one that Gauss figured out. So I'll write those ones, summation formulas. The first one is the easy one. When you're adding ones n times, 1 plus 1 plus 1 plus 1 n times, that is n. When you're adding integers themselves, 1 plus 2 plus 3 all the way to n, this is the formula that Gauss figured out when he was, they're saying it's 5 years old, 6 years old. I'm not actually sure this story is a true story, but it's a nice story to tell you guys, yes? Isn't this 5 years old could figure that out? And now I cannot see that. So again, the same story happens. The first one and the last one you add, and there are half of the total number of that many terms that you have to add. How about I squares? 1, 4, 9, 16, 25, 36, 49. If you add these ones, this is n times m plus 1 times 2n plus 1 over 6. How about I to the power 3? I to the power 3. This is very interesting fact, and I think this is a good learning for those who want to prove something. You have the feeling, yes? You want to do something that creates a bit better understanding on proofs. It turns out that sum of the cubes is square of sum of integers themselves. So this would be why is that happening? That's a very good question. There are millions of proofs out there. There are proofs without words. So if you are interested in those kind of things, you can find why this is square of that. And then there is also sum of geometric series or geometric sequence. R to the power I. I goes from 1 to n. So say R is 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and you add all these things. It turns out that there is a good formula for that. Which one I like to write, doesn't matter, both of them. So R to the power the upper 1 plus 1 minus R itself over R minus 1. So now we can use those to evaluate some sums of values. And I expect you to know these 5 formulas. These will be our starting point when we try to do Riemann sums for basic functions. And I need you to understand or remember these formulas. But let's do some examples. I goes from 1 to 10, 5, I to the power 3. The other one is 2I squared minus 3I plus 1. I goes from 1 to n, okay? And I like this last one. Sum of 3I squared plus 2 to the power I. I starts from 4, goes all the way to n. Let me do the first one, as I always do the easy ones. This is constant multiple. I can use that property and bring out that 5. What a 5. Awful 5. Okay. And see, sometimes you write things and you go back to read them. It's like, who did write these things? Or maybe that's only me experiencing that. That happens to me. Like, who did write this? Awful handwriting. I cube. Now, you first see I to the power 3. But you have to make sure that you also check that the indexing starts from 1 and goes all the way to a number. In this case, yes, indexing starts from 1, goes to the 10. So then I can use that formula that is given here for n equal to 10. So it will be 10 squared, 10 plus 1 squared divided by 4. And I believe you can simplify that and get to a number. Holy moly. I don't have any time to give you some time to do the other ones. Let us do something, because I wanted to do the iClicker question today as well. I'll turn on an iClicker question. But I want you to take that question for yourself at home, do it at home. But everyone is putting A as correct answer there. Everyone is putting A as correct answer. And then, do you see it? Yes? Do you guys see the question? Yeah? Can anyone confirm that it is posted already? Thank you. Okay, it should take you 10 seconds. Let me do this part. Here, now, I am adding those terms, but then I will use linearity of sigma notation, and then it will give me 2 sigma of I squared minus 3 sigma of I plus sigma of 1. I always goes from 1 to n. And for square, I have the formula. Now you have to know that. That is the result of the summation. This other one is n times n plus 1 divided by 2 times 3, and that is n. This other one has more points in it. You see that we have I squared 2 to the power I. So we are kind of working in this world. However, the starting point is not 1. These formulas work when the starting point is 1. How can I deal with that? Okay, so let me put this extra bracket. First thing is that let us rewrite this summation in form that j, the new index, starts from 1 rather than 4. Okay? So in other words, I have j is I minus 3. So that when I is 4, I get j is equal to 1. When I is n, I get this guy. Now, from that, I can conclude that I must be j plus 3. So everywhere I see I replace it by j plus 3, and then that one. Okay? Now, everything starts from 1. I need to expand these ones. So how do I do that? This, I can expand it and say, OK, this guy here is j squared plus 6j plus 9. Yes? And then I have 3 times j squared. That is 1 term. Plus 6 times 3, 18 sigma of j. J goes from 1 to n minus 3. The third one is 9 times 3, 27 sigma of 1. J goes from 1 to n minus 3. How about this other one? I can deal with 2 to the power some I index, but this is 2 to the power j plus 3. Just note that 2 to the power j plus 3 can be written as 8 times 2 to the power j. 2 to the power j times 2 to the power 3, but 2 to the power 3 is constant, so I can write this one as 8 2 to the power j. J goes from 1 to n minus 3. Now, I can use the formulas that I have here. The only difference is that instead of the ending formula, ending point n, I have n minus 3. In other words, this, which would be, if this was n, it was n plus 1, 2n plus 1 divided by 6. Now replace all n's by n minus 3. n minus 3. n minus 3 plus 1 is n minus 2. 2 times n minus 3 plus 1, that's 2n minus 5 divided by 6 plus 18. This guy, if it was all the way to n, it would give me n times n plus 1 divided by 2. But now, instead of n, I have to write n plus n minus 3. So n minus 3 plus 1, that one. This is 27 times n minus 3. And the last one is 8 times 2 to the power, the last one plus 1. 2 to the power n minus 3 plus 1 is n minus 2 minus r over r minus 1. You have to be able to do summations like this, evaluate it, and get it down to a formula in it. That is the first thing we will do in the Riemann sum. Have a great day, and see you all Monday. Or is any positive number? Could be 2, could be 10, could be half. Yeah.
It can't be negative because you just take the negative. It makes
Professor, how many people did it click to?
Around 12.
What's going to happen to those 12?